For this part of the video, we're going to review the three-part continuity test. As a reminder, here it is. All right, state how continuity is destroyed at the C value for each graph below. Okay, we can clearly see we have a jump discontinuity at x equals 1. So that means that part 2 fails. Okay, so you don't want to just say part 2 fails. You want to be more specific. You want to talk about the left limit and the right limit. So as I approach as I approach 1 from the left of this function, I guess we're going to call it f of x. Okay, if I'm approaching 1 from the left, I'm at the y value of 3. All right, the right-hand limit is I move back to 1, but I'm on the right side of it. I'm on the 5 piece, the y equals 5 piece. Okay. And so we can say, therefore, the limit as x approaches 1 does not exist. So part 2 is the part that fails. All right, how is continuity destroyed in this example? Well, the function's defined, the limit exists, but part 3 fails. Okay, so we know that f of 2 is equal to 7. We know the limit as x approaches 2 is 5. Okay, that's what the graph's coming into, even though the hole's here. So it's part 3 that fails. F of 2, that answer of 7, does not equal the limit. All right, let's take a look at example 3. State how continuity is destroyed. Well, I see the hole here, and I'm looking up and I'm looking down, but I don't see an included functional value, so I'm going to say that f of 2 does not exist. I don't have a y value when x is 2, so that's how continuity is destroyed. All right, for example 4, if f is continuous and if this is true when x doesn't equal 2, then what does the functional value have to be at -2? Okay, so what we're going to do here is we're going to actually find the limit as x approaches -2 from the left and the right. We're going to see what the graph suggests both the left and the right y values are going into. We're going to find the y coordinate of the hole, if you want to think of it that way. And once we know what the y coordinate is, then we can say that that's what the functional value should be. Okay, so that functional value kind of plugs up that hole. All right, so kind of the way you want to show this is, okay, as I approach -2 from both the left and the right, which means I'm on this piece, that's why I'm not doing a left and right-hand limit, because it's the same piece. When I plug in -2, I'm actually going to have indeterminate. All right, so I'm going to go ahead and, instead of factor, use my new rule, L'Hopital's rule. I'm going to differentiate the numerator, differentiate the denominator, plug in -2, and I'm going to get -4. All right, this answer is the same as if you were to factor this and cancel. Okay, and what this tells us is this graph from the left and the right, as I approach -2, the y values are going into -4, so that's exactly what the functional value needs to be in order that the function is continuous. So this should be -4. The question is, for what values of x is h not continuous? Well, looking at these pieces, they're all continuous on all real numbers. So the only case that we really need to consider is at the break, at the x coordinate of the break, where these two pieces come together. So we really have two test places: x equals -2, and then the graph transitions again at x equals 2. So let's start with testing x equals -2. And simply what I'm going to do is plug in -2 for both these pieces and see if I get the same y value. Okay, kind of informally doing the three-part continuity test. I mean, the first part says, is the function defined at x equals -2? Well, yeah, because of the or equal. here. It belongs here. So really we need to test just the left limit and the right limit. So I approach -2 from the left. I'm on this piece. So let's plug in -2, -6 minus 7, -13. Time to test the right piece. Well, that would be this piece right here. Insert -2. So that negative is just part of the term. -2 to the 4th is 16. Add 3. -13. So the functional value exists, the limit exists, and they're all equal. So yes, it is continuous at x equals -2. So the only place possibly where it wouldn't be continuous would be at x equals 2. So let's do that test. You're just going to plug in 2 to each of these pieces, see if they're equal. Formally, that's the left limit notation. So as I approach 2 from the left, on the middle piece, that would give -13. The right-hand limit, plug in 2 squared, 4 plus 9 is +13. So there's going to be a jump discontinuity there because this y value is at -3 and then this one's at -13, sorry. This one's at 13. So let's go back to the question. For what values of x is h not continuous? So let's make sure and answer that question. All right, so for what value of the constant c is the function f continuous over all the reals? All right, think 3-part continuity test. The function is defined at x equals 3. I guess I'm going to plug in 3 for both x here and x here, set them equal to each other. Formally, that's your left and right-hand limit notation. Plug in 3. Plug in 3 square root 9c minus 1. Therefore, let's equate the y's, make them equal. I'm going to subtract a 3c, bring it over here. Add a 1, make it 2. So it appears that c is 1/3. That would be the value of c that makes that continuous. All right, we're going to jump ahead to note card number 10. All right, so we're looking at differentiability implies continuity. And remember, it's not true the other way. I mean, just because a graph's continuous doesn't mean it's differentiable. Think the absolute value graph and you're good to go there. All right, look at number 1. Let f be a function such that, and you've got this long formal derivative here. That's a derivative. So I don't know what my function is. All I know is that whatever my function is, once I find the derivative, I want to evaluate it at 2. So this whole thing means what's f prime at the slope at 2? Well, we've got an answer. It tells us that the slope at 2 is 5. So the slope of the graph is 5. Which of the following must be true? Well, if I do have a slope at 5, meaning it's differentiable, then it has to be continuous. So I know there's a slope, so 1 and 2 are true. All right, now it says the derivative of f is continuous at x equals 2. The derivative is continuous. Well, I don't know any information about the derivative other than the slope of the graph at 2 is 5. I don't know any information beyond 2 to the left or to the right, so I can't say for certain that 3 is true. And because the question is must be true, okay, this could possibly be false, I'm going with C. Example 2, here's a new function. Oh, look at the k's in here. Ugh, and the p's. For what values of k and p will f be continuous and differentiable at x equals 1? All right, for continuous, we're going to be looking at the y values at x equals 1. So as I approach 1 from the left, I'm on the downward opening parabolic piece. Plug 1 in. 2 minus 1 is 1. Let's approach 1 from the right. Everywhere you see an x, plug in 1. So that's going to be 1 plus k plus p. All right, set those two equal to each other. You're very limited as to what you can do. You can subtract the ones from both sides. You're still not going to be able to solve for k or p since you have two unknowns with one equation. So that must mean we need to move to the differentiability idea. All right, we want f to be continuous and differentiable. So for differentiability, we're going to find the derivative of each piece and then plug in 1 to both derivatives. So the left slope, 2 minus 2x, plug in 1, you get 0. If I approach 1 from the right, I'm going to find the derivative, 2x plus k. Plug 1 in, and I'm going to get 2 plus k. Therefore, 0 must equal the right slope, 2 plus k, so k is negative 2. And looking back up to the continuity piece here, if I let k be negative 2, then it looks like p is going to have to be positive 2. So 0 equals negative 2 plus p. Yep, p is going to be equal to 2. And I think that's what we were asked to find, were the values of k and p. All right, let's see if we can get note card 11 in on this video. Looking at conditions that destroy differentiability, we had 3 of them. We looked for points of discontinuity. That seems in order. All right, then we talked about sharp turns, corners in the graphs, and sometimes these two are lumped together. Cusps are where the graph would become very, very steep, but not be a vertical tangent. For example, look at this illustration. If I had a graph that was decreasing, coming down like this, and all of a sudden stopped and turned around and was concave down this way, okay, this is a cusp right here. It kind of looks like a sharp turn. We put those together. A sharp turn is more, where you change from one piece to the other real quickly, like one line to another line with different slopes. But the third thing that did destroy differentiability was a vertical tangent. And as a quick reminder about that graphically, that would be where the graph's coming up and gets very steep and then turns around. So the tangent line right here is vertical. There's a tangent line, which is vertical. All right, question 1. All right, it's telling us that the graph has a vertical tangent at 2, 0 right here. So it's basically telling you that this graph is not differentiable at x equals 2. Horizontal tangents at 1, negative 1, and 3, 1. Question, for what value of x in the interval from negative 2, from here, to 4, is f not differentiable? For what values of x? So let's get our sentence prepared. Okay, as I work my way from left to right, we have a jump discontinuity, a point of discontinuity. So definitely not differentiable at x equals 0. Okay, definitely differentiable here, 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 but not at this vertical tangent. That's at x equals 2. I don't see any sharp turns or cusps, so I'm going to be finished there. All right, example 2. All right, great. Have another piecewise function. Show that f is not continuous at x equals 0. Prove that f is or is not, okay. Let's start with continuity. I'm going to approach 0 from the left. So I'm on this piece. Plug in 0, I get 1. If I approach 0 from the right, I'm on the bottom piece, and I'm going to get 4. Therefore, the limit as x approaches 0 of the function does not exist. That's going to be a jump discontinuity. Okay, well, I don't have to prove anything about B. Since A is false, B is false. So this is A and B. So just state it. If f of x is not continuous at x equals 0, then f of x is not differentiable at x equals 0. And that's it.